Welcome, 8th graders. Welcome back to Monday. Hope you had a good weekend. You'll notice if you looked at the Google Doc, I've cut this week a little bit short. I know you've been working hard, and I'm trying to give you a day off on Friday if you're staying on pace. Now, we also have 2 discussion boards that you're doing. Hopefully those are ways you guys can interact with one another, and we understand those pretty well. Now, Chapter 6, Lesson 1. Why do atoms combine? Well, we look at the atomic structure of atoms, and we get some pretty general stuff that we probably and should already know. The nucleus, it contains the protons and the neutrons. That's the atom's center, or the center of the entire atom. Then we have the electron cloud. That's the area of space around the nucleus where electrons travel. They define it as this area because we can't pinpoint where any one specific electron is. Now, if we're thinking about size comparisons, page 162, paragraph 3 has a nice one. If you were to put a penny on the center of that football field, the electron cloud would be as wide as the edges of that stadium and the same height and depth and all those other things. So that just gives you the sheer amount of size of the electron cloud compared to the nucleus. And that electron cloud is generally thought to be empty space, but because those electrons are moving so fast, that empty space makes very solid objects. Now, element structure. Neutral atoms have an equal number of protons and an equal number of electrons. 4 and 4. 4 positive charges, 4 negative charges. They balance out very nicely and very easily, and this is a neutral atom with no charge. Atoms can lose or gain electrons. Then you get, anyone know? Ions, either positive or negative. Positive ions are when an atom loses an electron. More positive charges than negative charges. Negative ions are when an atom gains electrons and you have more negative charges than positive charges. Those will come into play more next lesson and how these ions then want to combine. All right, now electron arrangement. Energy levels or steps. That's going to be this category. Number of electrons in that level. Electrons' attraction to the atom, so how tightly or close is it attracted to the atom? Electrons' amount of energy, so does it have a high level of energy or does it have a lower level of energy? The amount of energy needed to remove an electron from an atom. That'll kind of help us make sense of things a little later on. So we look at this first row. Energy level 1 or step 1. There's a good picture that'll come up at the end of this slide. It's from page 163, and it will kind of give you this in a visual. So, the number of electrons that can be in this energy level 1 or step 1 could have 1 or 2. Hydrogen and helium are the only elements that have this as their outer electron level. Now, the electron's attraction to the atom is the strongest of all because it is the closest. The amount of energy is the lowest because it is the closest. There's not as much outward force pulling it. There's less energy there. And we need the most energy if we're going to remove these from the atom. Now as we go out, step 2 or level 2, you can have 1 to 8. So 1 to 2 in here and then 1 to 8 in here. You would add these together to get the total. Now, it says in between and in between. Well, if this is the strongest, this would probably be the weakest, and these would be the in between going from strong to weak. This is the lowest amount of energy. This will be the highest, and going from lowest to highest, these will be in between. Now, we see that in between in all 3 levels. All right, so as we move to that third energy level, we're going to have the little bit less energy needed to remove them, even less energy to remove them, and then the least energy to remove them. The amount of energy, lowest, a little bit more, and highest. All right, strongest attraction, a little less, and then the weakest attraction. Now with energy level step 3, all right, it can hold 1 to 18 electrons. Again, the in-betweens, we talked about that in the previous one. And in our final one, energy level 4, 1 to 32 electrons can be held there. These two are content or stable if they have 8 in that outer level, but they can hold more. All right, notice, weakest attraction to the atom, because it is further from the atom, which makes sense. If it's further from it, it's going to have less attractive force. The amount of energy, it's the highest amount of energy because it's traveling at that fastest speed to get around the atom and orbit it. And we need the least energy to remove that. All right, because it's further away, there's less attraction, it is easier to remove these items. All right, so again, we see most energy required to move it, least, and these step down a little bit each. Lowest amount of energy needed, step up to the highest. Strongest attraction, step down, a little bit less, to the weakest attraction. We can go back to this and we can see the picture from the book. Sorry about the coloration there, the lighting wasn't very good. All right, in step 1, 2 electrons can be in this level, and you can see that level right in here. It is the closest. Now we're obviously doing a 2D look, not a 3D look. All right. Step 2 can have up to 8, and it's a little bit further out, and all this space in between is also included, but these levels are kind of generalized here. Then, step 3, energy level 3, we see right here, and it can go up to 18, as you see, and then that outermost level, we're going to go back to blue, is right here. All right. We really will only be focusing on ones that go to level 1, level 2, and a few that go to level 3, all right, the very earliest ones. We're going to look at that electron arrangement and why that's important. Now, electron configurations. Here's kind of how they pace out. I really suggest page 165. All paragraphs are very good. It's a lot of reading if I read it out loud to you, but I would suggest reading it. Now, if we look at that first energy level, hydrogen has 1, so it goes in that first level. Helium has 2 electrons, so 1 and 2. Oh, that first level is full, that outer level is full. Then lithium, 1 and 2. Then we jump to that third level. Beryllium has 4, 1, 2, and then 3, 4. After the first 2, we jump to the level, and you can kind of see the pattern continue until we fill. And the odd thing that happens, or hopefully you notice, neon has 8 in that level, that second level. That's how many it can hold. Then we jump to sodium, all right, and we start to fill that. We have our first 2, and then 8 more, that's 10, and 11. Oh, so 11th is there. Now, we fill that. Magnesium's got 2. Aluminum with 1, 2, 3 in the outer level. These are the Bohr diagrams, and they kind of talk about how we fill these levels, from inside to outside. These being in the inside have that most attraction. These being on the outermost have the least attraction to there and easier to remove. All right? Now, element families are something big that we'll describe. They usually have similar traits and characteristics, just like you and your siblings may look alike or act alike because of the way your parents have raised you. All right? They have the same number of electrons in the outer energy level. All right? So that's something that's important. And those outer energy level electrons really have a lot to do with why things combine. We look here, and here are some of them. We have the alkali metals. We have the alkaline earth metals. We won't talk about those as much today. We have the halogens, and we have the noble gases. Transition metals are also in here, and then we have this group that's right there. We will talk about those a little later on, but they don't get a family group name just yet with what we're studying. So, alkaline earth metals and transition metals are later. We'll learn about the other 3 families that are highlighted. All right, the noble gases. The noble gases are over there in group 18. All right, they go from helium down to radium. All right, we talk about them. Outer energy levels are stable. They have 8 electrons, with the exception being helium, it has 2. They have full outer electron shell. That means they have 2 or 8 there. That makes them non-reactive, all right? They don't easily combine, and you'll oftentimes see them by themselves. One use that they have, or 2, excuse me, they're used to protect light filaments, all right, in light bulbs, or in neon signs. Different noble gases provide us with different colors, as you can see there. Halogens. Halogens are that second group, group 17. With halogens, we need to gain 1 electron for them to be a stable outer level. That means they have 7 in their outer level. They need to get 1 more. They are fluorine, chlorine, bromine, iodine, and astenine. All right? They're a very reactive group. Fluorine being the most reactive, and they get less reactive as they go down. Because fluorine has a group that needs 1 that's closest, it has that most grabbing power, that most attractive force, and as you go out, these need 1 in levels that are further out, so they don't have as much of an attractive force. So fluorine is the most reactive, and it gets less as we go down through the group. All right? Many used in disinfectants, things like bleach, things like iodine. And if you remember from the Hunger Games book that you read with Mrs. Whalen, iodine was used to purify her water and get rid of all those nasty little things that could be in there. She used that iodine to do that. Hopefully you remember. All right, alkali metals. They're group 1. Notice, hydrogen not circled. It does have 1 electron in its outermost level, but it is not part of this group. It starts with lithium and it goes down, therefore. All right? It needs to lose 1 electron. So it just has 1 electron in the outer level. If it can lose that, then it goes down to a lower level that is full. With these, they're a very reactive group. Lithium is the least reactive because that outer element or that outer electron is closest to the nucleus and therefore hardest to pull away. As you get down the list, they're easier to pull away because they're in electron energy levels that are further away and therefore can take away from things easier. So lithium is the least reactive, and they get more reactive as you go down. So cesium being your more reactive one than any of them. Now, lithium-ion batteries, rubidium and cesium, francium used in electrical, sodium, yeah, you see it in the salt, potassium, and other items there. All right. So electron dot diagrams are the last thing we're going to talk about, and they'll be very important as we kind of move forward. What they are. It's the symbol for the element, so like hydrogen is H. So H would be the symbol for hydrogen, surrounded by as many dots as there are electrons in the outer level. Okay? We do this because they, the outer level, are most important in deciding how the elements react. So this electron dot diagram is a way to simplify things and say, oh, there's 1 electron in this outer level for hydrogen, or there's 7 electrons in the outer level for fluorine or chlorine. Then we can see from examples what is where. One thing before we go to our examples, in groups 1 and 2 and 13 through 18, the 1 place tells us the number of electrons in the outer level. Group 1, the alkali metals, they had 1 electron in their outermost level. Group 2 has 2 electrons. Group 13, if we look at the 1s, that's a 3. There's 3 electrons. 4 in the outermost level, 5, 6, 7 like we knew for halogens, and then 8 in the noble gases. Now, let me get rid of my blue dots here. When we look at these, hydrogen has 1, so its electron dot diagram, 1 dot there. Helium, 2 electrons in the outer level, 1 and then 2. Lithium with 3. Oh, that first level, 1, then 2 are filled. Then there's 1 left over for the next level, so there's 1 there. Notice that the 1 starts on that right side, and then we go right, top, left, right, top, left, bottom. And then we start the pattern again with nitrogen. There's 5, because nitrogen is in this list right here. And we put 1 there. Oxygen has 6 in the outermost level. All right. And fluorine with 7, neon with 8. 8 is what we want. 8 makes things stable and it's a nice arrangement for the atoms. That's what they're all trying to get to. So many times you're going to see those that have 7 and those that have 1 interacting, because they need to lose 1, they need to gain 1. Okay? So, those outer levels, this is row 1, this is row 2. Here starts row 13, row 14, because we skipped over all these rows here. All right, row 15, row 16, row 17, and row 18. All right, that's how we can know for these electron dot diagrams. And if I go back real quick, if I'm asking you to look at, excuse me, I've lost my train of thought. All right, we see these items here. If I'm asking you to look at those, you can know by their row and group how many they have, or you can simply fill in the inner levels and then go. Now, using the dot diagram, atoms combine to become more stable. That's why they do it. That means 8 in the outer energy level except hydrogen, which wants 2. The practice that I have for you today is we're going to look at their electron dot diagram. Now we see chlorine. Chlorine was in group 17, so we know it has 7 valence electrons or outer level electrons. So we put the 7 here. Now, something like sodium that has 1 would like to get rid of 1. Chlorine would like to gain 1. So what we'll see them do is there will be a sharing and those will combine and they become an element. Other examples, carbon. Carbon has 4 in the outer, or 4 valence electrons. Now something like hydrogen has 1. So how many hydrogens do you think are going to want to match up with this carbon? All right. Hopefully you guessed that there will be 4 of them. And when they do, each one of these dots up there. Now notice how the C has 8 around it, and the hydrogen, each hydrogen has 2. And that's what hydrogen wanted. And that chlorine, if we look there, the ones that it's sharing, it ends up having 8. So chlorine has 8, its outer level is full and happy. Hydrogen has 2, its outer level is full and happy. And they're both more stable. Okay? And all things are good for both of them. Now, we've done that little bit of practice here. I do want you to look at the next thing that's coming up. These. So, we already saw how 1 hydrogen was going to match with 4 of these. If I've got nitrogen, and I'm trying to match it up with hydrogens, how many hydrogens do you think we would want? Oh, there's 3 open spaces, so we put 3 hydrogens with that, and we'd have that match. Now, there's something else you might be a little bit familiar with. Oxygen matches with hydrogen. Now, there's 2 open spaces. Oh, this has 6 outer electrons, this has 1. Well, if I put 1 hydrogen, 2 hydrogens there, we come up with something called H2O. Maybe you're familiar with it. All right? Now, something like chlorine might very easily go with sodium. Or lithium. Would it match very well with fluorine, with having 1? Now, items like beryllium, it has 2 to give away. And something like sulfur needs 2. They might go together very well. But now we're getting into double and triple bonds, and that's going to be the basis of tomorrow's lesson. So, seeing a little bit of how it works, hopefully can help you out, and hopefully can get you through the work. Please don't hesitate to call if you have questions. Thank you. Goodbye.